All right. Hi, everyone. On such a sad day. It's my pleasure to introduce Belén Costanza, with whom I share deep sadness today. She's visiting us from Argentina, and she's a PhD student in her last year, and she is working, her supervisor is Claudia Scopola, and her co-supervisor is Matias Larreaga, who you might remember from here, but you're too young, but he's in IAS. And so Belén will be telling us today about deep learning applications in cosmology from the early to the late universe. And the floor is yours.
Thank you, Cecilia, and thank you for letting me to present my work. I'm gonna talk about the projects that I've been carrying out during my PhD, which is mostly focused on analyzing the CMB data. But also I work with large-scale structures, so I want to talk about these too because it was interesting for me to see how to use neural networks in both cosmological scenarios. So from the beginning, I'm going to start with my topic of my PhD thesis, which is the cosmic microwave background analysis. So just to motivate my work, we already know that the CMB is a very good approximation, a Gaussian random field, under the assumption of the lambda cold dark matter standard model. Can you hear me well, right? Okay, if I'm going over time, please let me know because I can talk so much. Okay, so the CMB we can consider as a Gaussian random field. The power spectrum carries all the cosmological information. So in our work, we ask ourselves how to estimate optimally the power spectrum. So can I have a... I cannot see it. Okay, well, I cannot see my mouse that way. But in the first image, no, creo que tengo. Sorry. Okay, it appeared. Okay, so in the first image, it's like the typical analysis to do with the CMB data, starting from the time order data that an instrument measure. Then these are all the steps, compression steps, until we estimate the cosmological parameters. And these compression steps is like a reduction in the dimension of the data. So this compression should be as optimal as possible in order not to lose cosmological information. So typically, I'm interested in this part from the CMB map to the power spectrum estimation. So far, the power spectrum of the temperature of the CMB is already well measured by Planck and also terrestrial instruments. But okay. But the CMB is also polarized because the radiation field has a quadrupolar anisotropy generated by the scalar and tensor perturbations, and when interact with the baryons through Thomson scattering, it produces linear polarization that is linearized. So in general, we express the polarization in terms of the E and B mode patterns because the Q and U parameter, Stokes parameter, are not scalar quantities under rotation. So for the power spectrum analysis, it's better to work with E and B modes. And already the E modes are also well measured by Planck and also instruments like ACT. But there is like a major cosmology challenge, which is measure the B mode pattern, because the E mode is mostly sourced by scalar perturbations in the metric of the universe, but the B modes are sourced by tensor perturbations. So measure these B modes will be like a way of measuring the stochastical background of gravitational waves. So there are several instruments right now that aims to measure these B modes. One is like Salmon's Observatory, another one like LIGHTBEAR and QUBIT, which is placed in Argentina. And the way of parametrize this signal is through the tensor to scalar ratio, which is so far there is only an upper limit that was measured by Sepp Geek. And there is a problem that the B modes, I'm putting in this plot here, is a very tiny signal compared to the E modes. So the polarization is mostly dominated by the E modes, and it's very difficult to measure these B modes for that reason. But these instruments, and also there are several ones that here I just put three, they wanted they wanted to reach the sensitivity to measure or expect to measure this remote, but it's not only an instrumental challenge, it is also a challenge in the analysis of the data to be able to have pipelines that could be able to detect these remotes. So I'm going to talk here about the Wiener filter. This is what I wanted to introduce now because I told you that I'm interested mostly in this part from the maps to the power spectrum, but these maps that comes from the time of the data to the map making contain noise and also contains foregrounds. But right now I will focus just in the instrumental noise. So I will assume that I have a CMB, the signal, plus noise. So the Wiener filter is the filter that reconstruct the underlying signal. This is the expression of the Wiener filter estimator. This S and N are the covariance matrix of the signal and the noise respectively. So we should already know in advance the statistical properties of the signal and the noise that we will have in your instrument. And this estimator is obtained through the minimization of the residual between the signal realization and the reconstruction. But in the case of the in the case of the Gaussian random fields, that is the case right now of the CMB, also coincides with the maximization of the posterior of the signal given the data. So that's why for Gaussian random fields, like in the case of the CMB, the Wiener filter is the optimal filter to reduce the noise and reconstruct the signal behind. So maximize the posterior is the same as minimize this chi-square function. So this system is usually, to obtain this estimator is usually solved through a linear system using the preconditional conjugate gradient, but this method takes a lot of time. So that's why in this work we studied if we can use neural networks to do this Wiener filter in a more efficient way, and then see if doing that we can obtain a better estimation of the power spectrum. So the loss function proposed right now is here written in terms of the maps. I put in the input will be Q and U maps, which is the observed maps of the polarization of the CMB, and the output we expect to be the Wiener filter of Q and U. So here is like the same as the chi-square function. I mean the loss function just written in terms of the maps, but it's this same chi-square. So if we minimize this loss function, we expect to obtain the Wiener filter estimator through the neural network. And the neural network proposed has this architecture. It is based in an already existing neural network called WienerNet, which is an autoencoder, proposed by Manchmeyer and Smith, but it's only for homogeneous noise, and it was written in TensorFlow 1, which is a bit old. So we write it in TensorFlow 2, but it wasn't something trivial to do, change the version of TensorFlow at that moment, because there was a lot of changes in the library that affects the performance of the neural network. And also, we wanted to extend to more complex noise models, so we also extend the neural network to also account for inhomogeneous noise. So the idea will be that we will have the input maps, which are going to be, for example, Q and U, or also can be the temperature. It's going through the unit architecture, and it will return the Wiener filter map. This channel that I put here in pink is a linear channel without activations, because the Wiener filter is linear with the data. That's why we didn't add in this channel nonlinear activations. But we also add two channels, one accounting for the binary mask and the other one for the variance map. In this case, we choose like a variance map coming from Planck in order to assess a realistic example. And these two channels have the nonlinear activations, and then multiply the linear channel to transfer this information. So I'm not going to talk here about the case of the temperature, because I am most interested in the polarization, because it's right now the goal in cosmology. So there was a problem also in polarization that it is called E2B leakage. Since we have in our maps the binary mask of zeros and one, there is a transmission of the E power into B modes. So, for example, if you make a map of the B modes for the observed Q and U with a mask, you are going to see ambiguous B modes that are not real B modes. So this was a problem because this leakage is in two ways. I mean, also P modes contaminate E modes, but the E modes are dominate the signal compared to the B modes. So for the neural network, it was difficult to separate the E and B modes. So we started training the neural network with these Q and U maps, obtaining the Wiener filter, assess the correlation because we can also calculate just for the test set, we can also calculate the neural, I mean, the Wiener filter, but with the conjugate gradient to see if we are obtaining the exact Wiener filter that we want to obtain, and to see if we are able to recover the Wiener filter of the B and B modes, the E and B modes. But at the beginning, in the first training, the B mode, I mean, the neural network wasn't able to find B modes. The neural network find mostly E modes. So we decided to make this iterative approach in which we generate now a new data set with the contribution from the first training, the E mode, just the part of the E mode, subtract from the data. So we generate new data set with less contain of E mode, and this allows the network to focus more to pay attention into the B modes. So you can do this as I mean these iterations as you want. I mean several as you want, but in this case with the 4 iterations it works. So it can be seen that the B modes were like most reconstructed during these iterations. Yeah, but this is like, I mean, I don't want to spend a lot of time in this part. I just want to say that the idea behind will be to estimate the power spectrum. So if we want to find the power spectrum, we should maximize the likelihood of the B-net power spectrum given the data, which is also expressed in a Gaussian. This is the covariance matrix of the data, which is the sum of the noise covariance matrix and the part of the signal. And the optimal quadratic estimator is the solution to this, but it depends of like the inversion of this covariance matrix of the data, which is very expensive to do because this matrix is not diagonal in either space usually. So that's why there are algorithms that avoid to do that. For example, the pseudo-CL algorithms, which is a very common one, used in CMB, that assume that this matrix is diagonal, is not as optimal as should be, but it's very efficient. So we investigate if we do this Wiener filter, how can help to estimate the power spectrum. And there is a paper of Euroselchak that relates the Wiener filter estimator. You can arrange these terms and write in terms of the covariance matrix, the inverse of the covariance matrix of the data. So if you replace in the optimal quadratic estimator expression, you cannot write the power spectrum as the estimation of the power spectrum in terms of the Wiener filtering. So the idea is if we are able to estimate, to do an efficient way the Wiener filter, maybe we can also do this optimal quadratic estimator without assuming that the covariance matrix of the data is diagonal. So this is what we do. I'm not going to talk here about all the steps in the formulas, but we also follow another paper of Euroselchak, which is an approach, a simulation-based optimal quadratic estimator. So we start for a fiducial cosmology. We assume a cosmology, but in reality, in experiment, we are going to receive a new map with an unknown signal. So we have to estimate how to correct the fiducial cosmology and obtain the true power spectrum. And this is expressed in this paper, how to do that. And these are the estimators. It's the same, it's like changing like a bit the terms, but it's the same as this one for the E and the B modes. and expressed in terms of simulations. So this Fisher matrix and bias are estimated through Monte Carlo simulations, considering this fiducial cosmology. And this is the part that is important to have an efficient Wiener filtering, because with the conjugate gradient will be unfeasible to do estimate this Fisher matrix, because you need, for example, like 2000 Monte Carlo simulations. But if you already train your neural network, that is trained, and of course takes time, but it's already trained, then you can estimate the predictions are very, very, very fast compared to the conjugate gradient. So you are able to perform this Wiener Fisher matrix and not bias in an efficient way, and then try to do this optimal quadratic estimator. Then after estimating this correction, the true power spectrum of the E and B modes will be the fiducial one that we assume plus this correction. So in this plot that I'm showing here is just the result in which I put the relative, the difference relative compared to the true power spectrum. I mean, we simulate the true power spectrum, and we wanted to see if with our pipeline we were able to estimate this power spectrum. And seeing this relative difference, we can see is this the orange one, it is unbiased, so we are able to estimate it. The purple one is the difference relative of the fiducial and the true power spectrum, which it is biased because it is by construction like that. And yeah, so through this method, we are able to obtain the true power spectrum. And we compare it with the pseudo-CL because it's the algorithm most used now. And in this plot, I changed the color, but here in yellow is the pseudo-CL estimator, and in blue is my estimation, sorry. So you can see that in yellow, the pseudo-CL estimator is more biased than my estimation. And we also see the error bars, I mean, the error in the estimation of the power spectrum. And in yellow, again, is the pseudo-CL estimator. In blue is my estimator. And we can see that the error bars are greater for the pseudo-CL on larger scales than our method of optimal quadratic estimator. But for smaller scales, it's mostly the similar. So the pseudo-CL mostly struggles on larger scales because of the presence of the mask, but on a smaller angular scale, it becomes really optimal. So, okay, so right now, this is not, is like the idea of what I'm doing now, that is extend our pipeline to curved sky, because all this pipeline was in flat sky, because we are using 2D images and assuming a flat sky, but we want to apply our pipeline to a real coverage map. So we tested with Simon's observatory coverage map, heat map, sorry, and the cubic one. And right now also we write the entire network in PyTorch. We found that it's more efficient, and making some changes in the architecture, but still a unit, we found that a better performance of the neural network. So the part that I show you here, it's not necessary to do it now, because it was like the previous neural network wasn't like the best, but right now in PyTorch, we are able to estimate the E and B mode from the very beginning. It's not necessary to do this iterative approach. But I'm not going to show these results because I would like to now change the topic to another work that I made with this project called DREAMS project, which is using large-scale structure simulations. And I'm talking here about this also this project because it was interesting for me to see that it's very different to work with large-scale simulations compared to the CMB, because as I told you before, as we consider the CMB a Gaussian random field, we know that the power spectrum should be the summary statistic that carries the cosmological information. And my work was focused on estimate as optimal as possible this power spectrum. But on large-scale structure, it's not the case, because due to the structure formation is highly nonlinear, the fields, the cosmological field becomes really not Gaussian. So the power spectrum is no longer the summary statistic that carries all the cosmological information. So it was interesting for me to learn also that how machine learning tools are helpful to extract information from these cosmological fields. I just put here a lot, there are a lot of papers on that, but I just put here some examples using that kind of, with these ideas. So in this case, is in the DREAMS project, which is called Dark Matter Astrophysics with Machine Learning and Simulations. So the idea is that with this DREAMS project, we have like a dream suite, which is a lot of simulations, aerodynamical simulations that are very expensive to run, but they are really run. So with this amount of simulations, we can do also machine learning. So the idea is that we have right now a large number of galaxies, so we can perform statistical analysis, and they change in these simulations. They vary the cosmology, the astrophysical parameters, and also the physics. The particle physics, because the idea was to change the dark matter model and see if with the neural network we are able to find signatures of these alternative dark matter models and see if they marginalize the baryonic processes and see if we can find an observable of these alternative dark matter models. So just to give a very brief idea, we test at the beginning with statistical properties of galaxy populations to see if we can estimate the wonder matter mass used in which the simulation was run. So we started with the summary statistic of the galaxy properties, use a multi-layer perceptron just to create a latent space, and then learn the full posterior with using a normalizing flow, and of the wonder matter mass given these summary statistics. And then we also wanted to see if we can also do that, but at a smaller scale using galaxies in individual halos. So we have like dark matter halos. We use a graph neural network to create a latent space and then learn the full posterior again of the wonder matter mass given the properties of each halo. Okay, no, yeah, this is just to show the same idea. These are the statisticals, these are the summary statistics starting from the histograms of the galaxy properties in each simulation. This is how we split the data set because we have 1,024 simulations. And this is just to represent the dark matter halos in the other case. So the results is of the normalizing flow is the posterior. This is 1 over the wonder matter mass. And we also do a feature, galaxy feature importance, in which we just train with one histogram, an histogram, but for each property alone. And we found that the gas mass the gas mass of the galaxies was the most informative one to estimate to do this posterior estimation of the wonder matter mass, even more than the total mass of the halos. So this is just to show that we started for the histograms, but we also use instead of the histogram, the first two moments of the distribution, the mean and the standard deviation, and we also find the same, that the gas mass, this is like the predictions of the 1 over the wonder matter mass. This is the estimation with the error of the distribution. And we found again that considering this determination coefficient, that the gas mass is the most informative one compared with the total mass of the subhalo, it was interesting because we know that if we change the model, the dark matter model from cold dark matter to wonder matter, it is going to impact the subhalo mass function because it's going to suppress at a smaller scale. But it was also interesting to find that the gas mass is very informative and even more than the total mass. As I told you before, we also wanted to see what happened at a smaller scales using dark matter halos instead of these summary statistics. And we found that just using the dark matter halos, we were not able to estimate the posterior, to estimate the water matter mass. So we add this information, we add the information of the galaxies inside the halo on top of the summary statistics that is like the mean and the standard deviation of the property in the entire simulation. And we gain something because you can see here that the R square is a bit larger than, for example, here, but it's not so much. And even for the case of the subhalo, total mass, we gain here also, but again, it's not so much. So we see that using at least this simulation that are full cosmological box, using single dark matter halos, we can obtain so much information. Maybe just gain a little bit. Okay, sorry for this interruption. I hope that my battery is gonna last, but it wasn't the case. So you told me.
It's okay, you can continue with them.
No, it was just my last slide was the conclusion, so I was able to give the talk, but just for the conclusions, I talk here about two different projects. First, of the CMB level, that we already know that it is a Gaussian random field, so we can use the power spectrum as the summary statistic. But it is, maybe the message that I wanted to say that it is needed also algorithms to estimate this power spectrum as optimal as possible, because the pseudo-CL works really well and it's very efficient, but on large scales is not as optimal as we would like, because the B modes are the primordial B modes are present in this large scale. So that's why we follow this path. But at the large scale structure level, it is completely different, because in this stage, right now we cannot use the power. We can use it, but we will need more techniques to extract cosmological information. So I was interested to see how do we, using like cosmological box simulation, aerodynamical simulations, we can use machine learning and specifically deep learning to estimate estimate the one dark matter mass. Estimate the dark matter model. And we found specifically in this problem, we found that the gas mass of the halos, in particularly, I didn't talk so much, but in particularly the absence of gas, the number of subhalos without gas was the tracer of the one dark matter mass in this using this neural network. So we don't know. Maybe I think it makes sense because of if you assume a one dark matter cosmology, you will have a suppression of a small k power that will delay the collapse of low mass halos, and maybe they will tend to accrete and retain less gas. That's why the network is finding this. But I don't know. We can see in the future if we could find an observable to constrain the dark matter models. And that was the idea. Thank you.
All right, thank you so much, Belén. Any more questions? Yeah.
Already asked.
Everyone else? Here, the cosmologist in the room.
Yeah, I have more question about the posterior model. Do you have any intuition as to why the tail is so flat? That's low. What's the low omega? Yeah. Low frequent.
Do you mean this?
No, it's like the normalizing for posterior practice is true. Yeah, like you have a flat tail, like.
Do you mean here?
Yeah.
Yeah, this is because we are using simulations that we have a lot of more simulations with one dark matter models than cold dark matter models. This is the one dark matter mass, and these are the simulations more like cold dark matter models because the mass is higher, and these are the simulations with lower lower, a lower value of the one dark matter mass. So these are more like simulations with the one dark matter cosmology. So this is like a prior. So we have more simulations with one dark matter mass, And that's why the network here is 1 over. That's why it's the opposite. So this.
Maybe a choice of this one, yeah.
No, it's not a prior choice. It's like how the simulation was run.
Yeah.
I mean, yeah, maybe I should ask the people that run the simulation why they do that like that. I think it was an idea of having like a uniform value of the water matter mass, but I don't know exactly all the details. But yeah, the thing is that I have more simulations with wonder matter mass than colder matter mass. Yeah, that's why I have this like a flat tail.
And do you find how do you find the graph encoding works? Like, how effective do you find it?
Sorry, which do you mean?
How effective do you find the graph encoders work?
In the graph encoders, it is the same. I also have this tail.
Yeah.
So it's more difficult for the network to distinguish at these values of the mass than in this case.
Okay, any other questions? On Zoom, any questions? No? All right, then let's thank Belén